we were here. Uh, so we started with the collisionless Boltzmann equation, uh, and the the fact that it sort of satisfies some sort of a continuity equation in the phase space. This F, you can actually think of it as the density of stars in the phase space, or you can think of it as the probability distribution of stars. Uh, so the probability distribution interpretation is more tractable to mathematics because uh, uh, then it's sort of a mathematical construct, whereas if you think of it as like the density in phase space, you need a big enough uh, volume in phase space in order for that to have particles or stars. Okay, so this is actually a huge topic. This uh, kinetics. This is called kinetics or kinetic theory because we are interested in velocity, the details of the velocity distribution of particles. Right. So then we also said that by using the Hamiltonian uh, formalism, we showed that it actually also satisfies some sort of an advection equation in phase space, that as you follow the particle trajectories in phase space, the distribution, the value of the distribution function f is does not change. So basically, this equation is just the Lagrangian derivative of f. As you follow the particle in the phase space, the probability density uh, is a constant along the trajectories. Uh, and then I sort of said that uh, we can use Hamilton's equations, Hamiltonian formalism, to describe to describe the collisionless Boltzmann equation, and so sort of derive equations which are simpler than the general equations because they use the symmetries. Uh, and then at the end of the last class, we were actually doing this Jean's theorem, which is sort of uh, integrating over the velocities to get something like the fluid equations. These are called the moment equations. So we had an equation which was like so this is Jean's theorems, right? Sorry, not the Jean's equation. So Jean's theorem says that if you construct any function of integrals of motions are these functions I of x and v, uh, which are conserved, right? A lot for the particles. For example, if you have spherical symmetry, the all components of angular momentum and energy, all of them are integrals of motion. So you can construct a steady distribution function, which is a function of those variables. So integrals of motions are functions of x and v only, not t. T should not appear here. Okay, and any functions of x and v which are conserved along trajectories of the particles satisfy the steady collisionless Boltzmann equation. Okay, so we did this. Then we derived, so we started with the collisionless Boltzmann equation and took the moments of the collisionless Boltzmann equation. So collisionless Boltzmann equation describes this thing f, which describes a probability distribution in the 6-dimensional phase space, x comma p or x comma v. But a lot of times we are not so interested in the full 6-dimensional information. So if you integrate it over the velocity dimensions, you get something like something that look like the fluid equation. So this is your mass conservation equation. In fact, this is identical to your fluid equation, right? So this is the 0th moment, and the first moment, if you do, you get this equation, which looks very similar to your Euler equation, the momentum equation, right? rate of change of bulk velocity. So right, this bar represents the integration over the velocity space. So this is right. So this is the definition of these barred quantities. So you have something which looks very similar to Euler's equation, but it's sort of the similarity is a little deceptive because this is not a scalar. Right? The sigma ij squared, unlike in fluids where it is a scalar pressure, this new sigma ij squared is the pressure in fluids. But here it's a symmetric tensor. So in a 3 by 3 symmetric matrix which has 6 unknowns. So there are more unknowns than equations. So which makes it not so useful first principles theory. Okay, but it is still useful because you can use observational information to get a sense of some of these quantities. Okay. Okay, so we'll start from here. Last time we figured out this problem of cutting off this. So I think the screen is fine now. The aspect ratio of this is like not quite the right one. Okay, so so how do we deal with this? Right, so this is sigma ij squared, and this is the definition. And you can actually see it's a symmetric tensor because if you interchange j and I, vi vj bar becomes vj vi bar. This is vi vj bar. So you know these two quantities are symmetric themselves. So sigma ij squared is a 3 by 3 symmetric tensor. So this full thing in fluids is sort of like pressure, or if you write in the tensor form, this is pressure times delta ij. Yeah, but there is only one unknown. Okay, so what do we do? So any symmetric positive definite tensor can be written in a diagonal form. You can diagonalize any positive definite symmetric tensor as you can actually write sigma ij squared equals sigma I square delta ij, right? But these, so basically these are called the principal axes, right? When you do moment of inertia tensor or any other positive definite tensors, you do the same thing, that it's always possible to orient your coordinate systems along the principal axis so that the tensor becomes a diagonal tensor. So it will be something like sigma 1 1 squared, sigma 2 2 squared, sigma 3 3 squared, if we use those axes. Right, but those axes need not align with your coordinate axis, like r hat, theta hat, phi hat. They need not align with those. So, so the way to actually measure these things observationally is to actually just look at the velocity distribution of stars and measure these correlations, and then construct this full tensor and then diagonalize it, and so you can actually find a nice little ellipsoid, right, which represents this. Okay.
So in 6 unknowns in the tensor, 3 of them are the principal axis themselves.
That's right. The directions of the principal axis, and the 3 can be the values along those. Yes. So there are still 6 unknowns because you don't know the direction of the principal axis. Okay. So we'll actually use this. So this is the portion that was remaining from the last time. Okay. So what we'll do today is actually some applications of the we'll do some applications of Jeans equations. Okay, so see the Jeans equations are vector equations, right? So you can use any coordinate system to write their cylindrical or whatever representation. Similarly, Boltzmann equation, collisionless Boltzmann equation is a vector equation. So you can use any coordinates to write those. But Hamilton's principle gives you a much, algebraically much nicer and elegant way of doing these manipulations. So rather than treating them as vector equations and then just doing all that tedious mathematics of going from x, y, z to r, theta, phi, it's better to actually start with Hamilton's equations and then do the manipulations. Okay, so let's actually write down so I'll actually show you. So previously, just before this, I showed that if you use Cartesian, like ij coordinates, and if you take the moments, you get the Jeans equations in Cartesian coordinates, essentially, right? I had those ij's; they were Cartesian coordinates, uh, but in a lot of cases, Cartesian coordinates are not the best. For example, if you are interested in, say, describing motion of stars near the sun, right? The galaxy is a spiral galaxy, a disk galaxy, and most of the stars are going in sort of close to circles. So a better coordinate system is a cylindrical coordinate system, right? So, and for example, for a spherical distribution like globular clusters and elliptical galaxies, a better coordinate system is a spherical coordinate system because you can employ more symmetries. Okay, so let's look at Jeans equations uh, in sort of we'll see spherical coordinates. So I'll do this example a little slowly, but others I'll just write the result. Okay, so then the idea is actually the same. So last time I had actually written the collisionless Boltzmann equation in spherical coordinates, right? I had started with the Hamiltonian. I just said dou f dou t plus p plus x dot dou f dou x plus p dot dou f dou p equals 0, and p dot and x dot or q dot were written from Hamilton's equations. Okay, so let's write down the spherical collisionless Boltzmann equation. So this I had actually written down previously. Let me just quickly write it down. So I'll just write down the full thing at the beginning. R squared sine squared theta dou f dou phi minus dou phi dou r minus p theta squared by r cubed minus p phi squared by r cubed sine squared theta dou f dou pr plus actually minus because there's a gradient of phi minus dou phi dou theta minus p phi squared by r squared cos squared theta sine cube theta times dou f dou theta minus dou phi dou f by dou p theta dou p phi is equal to 0. So this is the collisionless Boltzmann equation in spherical coordinates. All the terms are written out there, right? Now, these uh, are just, so this is just r dot, right, from Hamilton's equation. This is just theta dot. This is just phi dot. If you look at your Hamiltonian in this, these p theta by r squared, p phi by r squared, sine squared theta are just the time derivatives of the coordinates. Similarly, uh, this whole thing is pr dot, right? So it has the gravitational force, but it also has these pseudo forces, like the centrifugal forces. So you have to be very careful about this. Similarly, here there are terms like those. So this is nothing but, sorry, this is not p. This is not theta. This is p theta. This is p theta dot. This whole thing with minus sign is p theta dot. Similarly, this whole thing is p phi dot, right? So this is the total Lagrangian derivative of f using these coordinates is 0. Okay, now this is the collisionless Boltzmann equation. What we'll do is we'll take moments of this equation. Okay, so PR is equal to R dot equals VR. Just to sort of refresh your memory, P theta equals R squared theta dot equals R times V theta, and P phi equals R squared sine squared theta phi dot, which is equal to R sine theta times V phi, right? This is all standard stuff. Okay. Let's assume the system to be spherically symmetric. So phi is only a function of small r, right? That's what we are assuming. So it's spherical symmetry. So a lot of these terms actually go away. Let's see. What remains is, so this goes away because dou phi is 0. This guy will of course go away. Okay. So let's take the moment now. So let's do PR. We take the above equation and do this integral PR dPr dP theta dP phi, right? So above equation, this equation, collisionless Boltzmann equation, we just take this moment, right? So this is sort of getting the radial equation of motion. We are not doing the 0th moment. That's actually easy. That's just the continuity equation. And the form of the continuity equation in any coordinates is very simple, right? It's the same as the fluid equation. So you'll have 1 by r squared dou dou r squared rho v, so the equivalent of that. But here you'll have some terms which are a little surprising. Okay, so let's see. And we also assume a steady state. So in a steady state assumption is very good for things like, describing old systems which have relaxed, like our the distribution of stars in the solar neighborhood. They've been around for a long, long time. They've had many sort of times to smoothen the distribution function in the phase space. Okay, uh, this topic is actually extremely subtle in the sense. So I actually had shared a little link which talked about distribution function and something called phase mixing, stochastic mixing in the phase space. The point is, last time I gave you this example, right? If you consider people standing and they are just running, I gave you this little distribution function and it was just sheared. So in general, the evolution in phase space is such that whatever initial distribution you take, it gets sheared a lot in the phase space. So, wherever you go near the trajectory of the particles, the value of f remains the same, but the distribution function in the phase space gets extremely sheared. And if you wait long enough, it gets so much sheared that at small scales there are large variations. But if you think of it as some sort of a coarse-grained distribution function, it is okay to. So we have in our mind some sort of a coarse-grained distribution function when we are talking about these distribution functions now. Okay, and this coarse graining is what sort of allows you to take f as a function of energy and things like that. Like a real distribution function can be extremely grainy, like you can have very large variation at small scale. We are not talking about that. We are assuming that the system is ergodic and the distribution function does not vary a lot as a function of position in the phase space, right? And there are processes like phase mixing, uh, and stochastic mixing that ensures that the f does not vary wildly as a function of coordinates in phase space. So this is an extremely subtle topic actually, and non-intuitive too. So just be aware of all these assumptions. Okay, so let's go back here. This is what you want to do. So we are anyway steady, so we just ignore this term. Okay. So yeah.
Is it possible that a coarse-grained distribution function time gets like shared into a much finer?
Absolutely. If you have a coarse-grained distribution, so if you have a localized distribution function, it will get sheared and become small scale. But what we are assuming is that, uh, when you're measuring a distribution function, you're sort of smoothing over those scales. Okay. So a system like galaxy and so on, we are assuming that uh, the stars in the same neighborhood in phase space uh, are have similar, the distribution function does not change wildly from location to location. They have sort of become ergodic in some sense. Okay, all these are actually very subtle things, and there are theorems and stuff. It's a topic in itself in mathematics. So it's sort of a lot of communities are interested in these kind of questions. And for astronomy, it's sort of a much more practical application, but the foundations of this are like in statistical mechanics and the Boltzmann, the formal aspects of solutions of Boltzmann equation. Okay, so let's go back here. So let's look at this first term. So we want to take the moment of this. So this is nothing but the first term. Basically, let's look at this. P R. So this dou dou R can come out, right? Because so PR square F dpr dp theta dp phi, right? This is fine. This is the first step, but this is nothing but r squared from above. So r squared sine theta dvr dv theta dv phi, right? So what does this become? So this is equal to r squared sine theta. That just comes out of the integral, and we have uh, PR squared, right? So we have, or VR squared, right? So this is the first term. PR is equal to VR, right? So this is the first term. Okay. Then let's see. This, of course, we are making zero. We are assuming axis symmetry. Tau f by tau theta term. Right. So what happens to that one? That's PR p theta by r squared dpr. So this is also f dpr. There is tau by tau theta. Right. So this tau by tau theta can come out because p theta and r both are independent variables. So this is this integral dp theta dp phi. That is just uh, that's just tau tau theta of actually there's a nu here. Yeah, since this nu is always there. Nu is like the number density is always there when we do this. So tau tau theta of nu r sine theta p theta vr. This is what we have. Yes.
So we can take the derivatives outside the integral because you are saying PR and P theta are independent.
That's right. So in this description, r theta phi, pr, p theta, p phi, and t. These are all the independent variables, right?
dp or dp theta velocity integral.
That's right.
Additional factors of r is coming.
Right. So, but they are inside they are inside this guy. They cannot be, right? So there is a subtlety. That's why you want to have this tau tau r squared inside that bracket. So what I'm doing right now is all mathematically fine because P is independent of R, so it can go inside and outside. But when you go to V, there are these extra R squareds which come. So that's what I'm saying. This whole Hamilton's approach makes all taking care of variables very easy. If you go brute force, you can take a full day in just doing one of these integrations. It's it's very tedious. Here, everything is actually clean. So this is the second term. No, p theta equals r v theta. So this is actually very important. Similarly, p phi is r sine theta v phi. This is actually very important. I mean, this is the Hamilton's, the Hamilton's formalism. Okay, so this is the second term. Okay, let's look at this guy. If we do the integration of this, what do we get? So minus tau phi tau r minus p theta squared by r cube minus p phi squared by r cube sine squared theta pr dou f dou PR PR dpr dp theta dp phi. Okay, this is the next term that we'll have. Okay, so we'll do these terms separately. So if you just look at this guy first, that's just DDR. What you'll do is you'll do integration by parts. You'll take PR inside and make it a total derivative. And by saying that PR times F vanishes at the boundaries, because F, the distribution function, should vanish at large values of PR, right? And the second term, so the term that you'll get, this guy will give you is F times a negative sign, right? Because this, then you'll have integration by parts will give you, you'll have to take the derivative of this, and that will give you 1. So you will have, the first term will become d phi dr times nu, actually. That's it. When there's a lot of maths, this becomes a little too much. Right, so this is this term, right, with the negative sign because of that integration by parts. And there is, when we go to VR, V phi, V theta, you'll have R squared sine theta multiplied, right? That will come here. So this is just the first term here. The second term, essentially you have to do the same thing. Integration by parts, what you'll get is, let me just write down, minus, so right now there is minus minus, this becomes plus, but then we do integration by parts, we get another minus. So this is minus of nu R squared sine theta by R V theta squared plus V phi squared bar. This is what you get. Okay, you can actually see, it's just easy to see. Okay, so writing down the terms and simplifying it, what do I have? I have, right, the other things, let's see, this guy, let's see this one. So you have PR, and if you integrate this over P theta, this just vanishes, right? Because there is no P theta dependence here. It's a total derivative in P theta. And I say that at large values of P theta, F has to vanish. So this gives nothing when you take the moment. I mean, it's a little subtle, so you have to go through these things on your own and convince yourself that this is indeed what you get, okay? So this gives you the final equation. So let me write that down. Okay, so this is dou dou R nu VR squared plus, right? So there was this R squared in the first term. You remember there was this R squared. Now you have to take the derivative with R, so it will give you 2R term, right? So that would be plus twice nu by R VR squared. Okay, and then we have plus dou dou theta one by sine theta. This one, this guy, basically nu R sine theta VR v theta. I hope I'm dimensionally correct. VR squared, so there, I think there will be an R squared, so there will be 1 by R outside. Okay, now what I'll argue is this is 0. This VR v theta bar will be 0, and I'll actually show you why that will be the case. So let me actually just write the other terms as well. Plus nu d phi dr. This is this guy, and minus nu by r v theta squared plus v phi squared bars is equal to 0. So this is the moment equation. Okay, now my f, I have said, so this is a spherical system. Okay, so what are the conserved quantities in the spherical system? Steady, it's steady, so nothing changes in time. So v r squared plus v theta squared plus v phi squared by 2 plus phi r. This is your Hamiltonian. That's an integral of motion because the potential is independent of time. What else is conserved? The magnitude of angular momentum is conserved. So that's what. So what's the magnitude of angular momentum? Right. That's nothing but r times v theta, v theta squared plus v phi squared. Right. So so I'm actually assuming the distribution function to be a function of this only. Okay, this is an assumption. In reality, it may or may not hold. But if I assume this, you can actually see that if I take this VR v phi bar, that's so nu VR v phi or VR v phi bar is actually integral VR v phi f d3v, right? Times nu. And you can see if it's sort of this is a symmetric function of VR, v theta, v phi. It's a function of v squared, vr squared, v phi squared, v theta squared. So just by symmetry, you will see that these odd powers will give you 0. Similarly, there is no mean velocity. This is 0 because it's an odd function. Similarly, v theta is 0. V phi is 0 because these are all odd functions, and this f is an even function in velocity. So when you do the moment, just because the function is antisymmetric, the integrand is antisymmetric, you should get 0. The other thing that you can actually see from just this functional form is the following, that v theta squared bar is equal to v phi squared bar. Do you see this? Because the dependence in f on v theta and v phi appears like together, right? So you can just from that symmetry, if you do that integration and do a little bit, you will see that this has to be true for irrespective of what your distribution function is. Okay, so this is we know, and that's just sigma theta. That's right, sigma theta squared is equal to sigma phi squared, and these are equal to sigmas because the mean velocities are 0. But this is not equal to, in general, and this is not equal to VR squared, right? Do you see this? Because there is VR square appearing here, which is at the same footing as v theta v phi, but there is no VR squared here. So just from the form of your f and from the symmetries, you can actually gather so much out of these equations. So your Jean's equation becomes this one. So you can just get rid of this, right? So you have this, this, and that. Uh, and these two are actually equal. So you can just call it as V tangential squared, right? This can be just written as V tangential squared bar. Tangential, perpendicular to the radial direction. Okay. In fact, it should be 2 times V tangential squared. So if you take or let's see. Okay, now I think it's better to call it V tangential because they have to be added together. Yeah. Okay. Okay. So what do we have? We have. So what we have now is 1 by nu d dr of nu vr squared. I mean, this is just sigma r squared to this plus. So now I'll actually combine uh, this term and these terms. Okay, because they have the same like nu by r type of a thing. So plus twice beta times vr squared bar by r is equal to minus d phi by dr. Yeah, this almost looks like your hydrostatic equilibrium equation, right? This guy and this guy. But this is the subtle part. This is where this fact that it's not pressure, the pressure is not isotropic, comes in. So let me actually define what beta is. Beta is nothing but beta is 1 minus v tangential squared by twice vr squared. These are bars, right? It's sort of an anisotropy parameter, right? Anisotropy parameter. You are allowed to have velocity anisotropies even if you're spherically symmetric, right? So if Vt squared equals twice Vr squared, this becomes 0. If the velocity distribution is isotropic, if that ellipsoid is a sphere, in other words, that sigma ellipsoid that I was talking about, then this equation just becomes your hydrostatic equilibrium, right? dP dr equals minus rho g, correct? But in reality, you have this extra term in the force balance equation, which is due to anisotropy. So we can actually do some further manipulations. And we can actually, so here it was just number density in real space, but we can actually just might as well convert into mass density. If if we assume all stars are the same mass, it's sort of a trivial conversion, and this becomes, where did it go? This becomes rho 2 in that case. Okay. And this is nothing but, this is equal to minus g m enclosed r by r squared, right? This is just gravitational acceleration. So by looking at your velocity spreads and the anisotropy of your velocity, of your dispersion, velocity dispersion, you can actually calculate the enclosed mass in a spherical system. So let's write down. So mr is equal to, so I'm just sort of manipulating this equation. So this is equal to minus r squared by g or like rather than writing even one more intermediate step, let me just write down the final step. So minus r sigma r squared, that's just vr squared bar. They are equal because the mean radial velocity is 0. This times d log nu by d log r, which is the same as d log rho by d log. This is just the logarithmic slope of the profile, the density profile, uh, plus d by d log r log sigma r squared plus twice beta. What I've done is just the same equation that's written up there. I've just rewritten it to write this, and then I've taken r squared there, and I've introduced these logarithmic derivatives. They're like the local slopes, right? 1 or 2 or something, their values will be order unity. You can actually measure these things. This is a measurable quantity in a spherical system. This is a measurable quantity. The tangential velocity is distribution is a measurable quantity. So all these things are measurable quantities, right? From say line of sight velocity distribution, or so if you're looking at an external system like a globular cluster, your line of sight velocity distribution will give you sigma tangential actually. If the globular cluster is like it will give you sigma tangential. Uh, and if you have some sense of beta, then you can actually use this equation. The radial velocity also, if you have like a spatially, if you have a spatially resolved globular cluster, then the radial velocity just can come from the center observation of the center of the globular cluster, because the stars will have, the radial velocity is what you see. If you're looking at the edges, uh, you can get the tangential velocity, and then, cleverly combine them to get all these things observationally. The ultimate aim is to be able to get these things observationally and then calculate MR. So this gives you a way to get the mass modeling, say for a globular cluster or an elliptical galaxy or a spheroid system, right? So this is how you can infer the presence of dark matter, for example, right? If it were just, if beta was 0, then this is just hydrostatic equilibrium, right? These two terms are just dn dr and dt dr kind of terms, okay? Um, let's see. So you can apply these to globular clusters and spheroid galaxies and things like that. Okay, this is good. So this can actually, this formalism can help us know whether there is dark matter or not, for example, in a spherical system. So a similar sort of a statistical distribution is actually used for inferring the black hole mass. In a lot, like in Sagittarius A star, in our galactic center black hole, we know the mass from the direct orbits of stars. But if the galaxy is a little far away, uh, and you don't have as much resolution to actually see the Kepler's orbits of innermost stars, then what do? You measure their sigma squares and density profiles and so on, and use something like this formalism from using the statistics of velocity distribution of stars. Then you infer MR, and if you get a profile of MR which is constant as you go inside, that means that there's a point mass out there. So things like that. So this is like statistical inference of the black hole mass. These kind of methods are used. Okay. Okay, so this is one application of Jean's equation for spherical systems. We can actually also, we'll actually do, so this is number one. So we'll actually do one more application, which is something called A symmetric drift. Asymmetric drift. So this is an application uh, to the motion of stars in the neighborhood of the sun. Okay, so this is the coordinate system that will be more useful here is the cylindrical coordinate system, because you're looking at stars near the sun and they are almost circular orbits. So let me actually not go into deriving this now, because I've outlined how you do it. Same thing you apply in cylindrical coordinates. Let me just write down the equation. Okay, so this is the equation of motion for I mean, basically this is the Jeans equation in cylindrical coordinates. Rho v r. So rho and nu are sort of interchangeable. Plus r dot z v r v z bar. Okay, so what we are doing is we are applying basically this is radial equation of motion. You can actually see, and we are applying it at z equal to 0, right? So we are looking at the near the solar disk. We are just taking the distribution in z equal to 0. Okay, so there is, in the same way as in the spherical case, we have VR squared minus V phi squared plus R d phi dr is equal to 0. So this is the equation that we will get. Uh, now, in the rotating system, what are your integrals of motion? Of course, if your Hamiltonian is preserved because phi is independent of time, so what is your f is a function of vr squared plus p phi squared plus vz squared by 2, and it's a function of lz. Lz is a conserved quantity, so lz is what? So r times v phi. These are two integrals of motion. So if you assume that these are the only integrals of motion, so this is a big assumption, but if you assume that, then it gives you a lot of information about what. Hmm? Right, sorry. Yes, phi. In fact, phi r z. If we are, I mean, here we are applying it to z equal to 0, but in general, if we have an axisymmetric system, then the dependence is on r and z. So here you can actually see from symmetry also that VR squared. First, you'll see that VR mean is equal to VZ mean is equal to 0, right? Because again, these are even. This is an even function, but V phi is not 0. In fact, this is a very big quantity. This is right. It's sort of mostly circular, circular orbit. So V phi bar, the bulk velocity cannot be 0 for this system. So V phi is there. So we can actually write V phi as V circular You remember the definition of circular velocity. Circular velocity is if you have a test particle which goes in a circle in a given gravity. So this term is actually, this is just g, right? This is r times capital R times g. So this is just vc squared, right? Circular velocity just gives you a sense of the depth of the gravitational potential. It's not really the velocity of the particle. If there was a test particle that was supported by circular motion, that's the velocity of it. So it just gives you the depth of the potential well. So that's that. So let's just call it Vc minus Va. This Va velocity is called the asymmetric drift velocity, and this is what we are after. This is asymmetric drift velocity. And this is what, so basically the stars like the sun are not going at the circular velocity, right? They have some random motions on top of that circular velocity. And that random motion and its anisotropy causes it to have a slightly slower rotational velocity than the circular velocity. And we'll see that from this Jeans equation. Okay, so that's where we are going. Okay. So this is V phi squared. So let's see. So V phi is equal to V phi squared um, mm, plus sigma phi squared, or sigma phi or sigma phi, same thing. So the V squared bar is equal to the bulk velocity squared plus the random velocity in the phi direction squared. Okay. Uh, so what do we have here? Right. So these two terms actually combine you to give you Vc squared minus V phi squared. Vc squared minus V phi squared bar. So what does that give you? Vc squared minus V. This is equal to, so sorry, not this is V phi bar squared. Okay, so Vc squared minus Vc squared minus V phi bar squared minus sigma phi squared. Okay, and so this is actually equal to Vc minus P phi bar times. So Vc, yeah, Vc is just known times Vc plus V phi, right? A squared minus B squared equals A plus B. So, but Vc and V phi are comparable, so we can just write it as twice Vc. Okay, this difference between the circular velocity and the velocity of the sun or the nearby stars is not large. They're sort of comparable. So when you add them up, you can just take them to be equal. In fact, not phi, but c. Vc is a simpler quantity minus sigma phi squared. So if we plug all this in this equation written above, and the other thing that you can actually see is, let's see, VR VZ bar. This will actually be 0, right? You can see from symmetry. This will just go away from symmetry of these. So these are not strictly correct. So you want to measure VR VZ distribution and actually obtain the VR VZ bar from observations. Okay, but you can actually see it will be a small quantity in any case. Let me write down the first equation now in a form. So twice VC VA approximately VR squared bar times, what's the time by the way? 12:40. Okay. Sigma phi squared. I mean, this is really annoying. It's sort of, but by B R bar minus 1. So what I'm doing is I'm taking this term. This is this term which I have combined. I'm writing this as VC squared minus V phi squared as this, and I'm taking and this VC minus V bar is nothing but my asymmetric drift velocity, right? Yeah. Yes. This one to this line, right? What I'm saying is VC and V phi bar are differing by a small amount. So it's A squared minus B squared. If A and B are comparable, is equal to A minus B times A plus B, but A plus B, A and B are not differing by much, so you can just write it as 2A or 2B. It's like, uh, 2 squared minus 1.9 squared, right? That form. We are taking 2 VC actually. Why? Because VC is a known, we know VC for the sun, right? Okay, so this is minus 1. So this term is this minus 1 here. This term. And then you had the sigma phi term which goes on the right hand side. I don't know what is happening. I'm just. Is it really an internet problem or is it something else? But or is it this app becoming weak when there is a little bit of writing? So this minus 1 minus dou log by dou log r rho. I mean VR squared bar. So this is this term, right? I'm writing this term, and I'm actually just taking the dimensional part out and writing terms in this bracket which are order unity, right? Like logarithmic derivatives and ratios of velocity squares and things like that. Minus r by VR squared Yeah, this because I'm taking VR squared bar outside, so I have to divide it by that at a lot of places. Dou z of vr vz. I mean, I've retained it here uh, because, as I said, this is if if f was the function of these two only, this is not true for a real f. It will never be a like such a strict function, but it will be close to that. So this term will actually be small, but this is a measurable thing. You can look at the velocities, motions of the stars in the solar neighborhood, and actually calculate the correlation between the radial and the z motion. Okay, so this is how you get the asymmetric velocity. So you measure these velocity fluctuations in the radial direction, in the phi direction. You look at the how the density changes as a function of r. You see how the velocity distribution changes as a function of uh, radial distance from the galactic center and so on. Okay. Right, so this is actually small, so we can, to our thing, we can make it 0. This is about, if you plug in the numbers from observations, this is about 5.8. Okay. So this gives you VA in terms of these things. The other thing that I want to to tell you is we were doing this epicyclic motion, right? I had said that although in a single epicycle, the phi amplitude is double, is larger than the radial amplitude. If you look at the velocity distribution of the stars at the solar neighborhood, measured at the solar neighborhood, the radial velocity fluctuation is actually larger than the phi velocity fluctuation. That's because their guiding centers are different. You remember that discussion, the epicyclic theory and all that. So this is actually related to that, and it has to be. We are talking about the solar neighborhood, right? So let me actually write down what we had there. So uh, v phi squared right, or sigma phi is better. This is the fluctuation. Sigma phi squared by v r squared bar was about minus b by a minus b in terms of their root parameters. A is positive, b is negative. And if you plug in the numbers for Milky Way galaxy, this is about, in our solar neighborhood, this is about 0.45, right? So the radial velocity fluctuation is larger than the phi velocity fluctuation. Okay. Uh, and the other thing is sigma phi squared uh, right. So this is equal to v v phi minus minus vc whole squared minus va squared. So this is the asymmetric drift velocity value. I mean, there are little subtleties. The thing, so there is vc, there is v phi bar. They are not exactly the same. They are similar, but they differ by this va, which is small. So if you do all this, and if you plug in the values for sigma phi squared by sigma r, or vr bar squared, right? Then you sort of get you can actually measure the asymmetric drift velocity. Uh, Sigma phi squared. What about the z velocity? Because there is also this uh, z velocity. Yeah. So there are more subtleties which I'll actually not go into. But let me just write down. Uh, so what do we need? So this we have ignored. What we need is some sort of a density profile, right? And a disk galaxy density goes like an exponential. So rho is like e to the minus r by rd or something like that. So that can actually help us here. So rho can be written as rho naught e to the minus and vc, we know the circular velocity is about 220 kilometer per second. We have this ratio from here. Uh, we will get this from this. So if we if we just sort of put in the numbers for these geometrical quantities, these are geometrical quantities, like this is the shape of the velocity ellipsoid, this is the logarithmic profile of your radial pressure, essentially this is your radial pressure in stars. So what you get is VA is equal to VR squared, okay, bar divided by some 82 plus minus 6 kilometer per second. So this is your asymmetric drift velocity. This 82 plus minus 6 comes from these numbers. So VC is about 220 kilometer per second. So 220 divided by 5.8 times 2 is roughly about that much. Okay. So what you see here is that the asymmetric drift velocity is larger if VR square is bigger. If the random motion vertical, the radial random motion and vertical random motion, which are sort of expected to be similar, which is actually not. The measured Vz squared is similar to V phi squared, apparently, but it's not equal to the uh, V, right? So from the symmetry, we expect Vr squared to be equal to Vz squared, but what we see is that Vz squared is actually similar to V phi squared. What it means is this assumption of f just being a function of uh, this guy is not correct, right? From this, you can just infer, deduce that those have to be equal. Okay, so this is the asymmetric drift. So let me actually ask you guys a question. So we had learned about this thin disk and the thick disk of stars. Which of those stars do you think will have a higher asymmetric drift velocity, and why? So there is a thin, right? If you recall, in our first few lectures, we talked about Milky Way. So there's a thin stars. There's a thin disk of stars, and there are the thicker components. And the thicker components are the older components, which have gone around many times and have been scattered by molecular clouds and so on. Which ones will have a larger asymmetric drift velocity, and why? Make a guess. It's simple. Yes, the thicker disk has larger vertical random motion. Because of that, it will have a larger asymmetric drift. So it will be going slowly compared to the circular velocity. Okay. What's the time? Okay. So we'll do the third and last application. That is something called OOT limit. So
Change the file name.
yeah, I think that perhaps that's a good idea. I'll do it. Good idea. Uh, yeah, I think this is perhaps. Oh, I don't know. I don't think so. Let's go back. Uh, I don't know. It's just a okay. OOT. OOT limit. Okay. So you've heard OOT's name so many times. He is like the pioneer of galactic studies. So here we meet him again, and this is related to uh, he inferred presence of dark matter from measurement of, or invisible matter. He didn't quite like infer it as we know it today, but presence of invisible matter near the stars of stars near the sun. Okay. Let's get there. And the route to this will be again Jeans equations. So Jeans equations are actually practically very, very useful. Okay. So let's look at the cylindrical Jeans equation, and let's ignore this VR. VZ. I told these are, this is expected to be small, so let's just ignore this. This is set to 0. Okay. So what do we have? We have, if you look at the vertical moment, Vz or Pz moment of the Jeans equation, so you'll get an equation of motion for the vertical direction, right? So that would be so dow I dow z rho vz squared bar rho dou phi dou z equals 0. What is this? This is basically uh, just the hydrostatic equilibrium in the vertical direction, right? And this I've said, there are terms which involve VR, VZ, but I'm setting it to be small because, from symmetry, uh, VR squared, VZ squared appeared. And so the correlation, the linear terms on integrating over velocity will give you 0. Okay, so this is a vertical hydrostatic equation. But we also have the Poisson equation, right? You have now 2 pi dou z squared pi uh, plus 1 by r dou by dou r dou. Okay, so this equals 4 pi G rho. This is rho total, all the mass. Right. See, this rho can actually be rho due to some tracers. Like this can be just some, say, what he used was F and K stars in the neighborhood of the sun. This equation applies to all like subspecies. You can have a subset of stars which will satisfy the collisionless Boltzmann equation and the moment equation. Whereas this phi here is the external, the total potential, and that is dominated by not only these stars but mostly by other mass components. Okay, so that's why it's important to distinguish this density and this density. Okay. And for disk systems, we know that this is small, right? We had done this plumber and all this, and learned how to deal with the disk systems. The Z term is much bigger than the radial variation term because the radial variation is small. Uh, because these are disk systems, so we are looking at stars near the Milky, our location in the Milky Way. So if we use this equation, what do we get? So dou phi dou z, and if you do another derivative of this, in fact, it's better to perhaps use nu, so as not to confuse with d by dz of nu vz squared bar ddz. This is the first term in the Poisson equation, is equal to 4 pi G rho total. Okay, you see these are measurable quantity, Vz squared, number density of stars, and so on. But if you have a noisy measurable quantity and if you take a second derivative of it, it's not a good idea, right? The derivative enhances all these errors. So what you do is you integrate it over Z and write it in terms of the surface density. Uh, what you get is 2, and you assume symmetry in plus Z and minus Z, so 2 pi G sigma, this is the right hand side, less than Z is equal to 2 pi G, right? Of course, this is minus Z to plus Z rho Z prime dz prime. This is equal to minus 1 by nu d dz nu sigma z squared. Okay, so what did Oot do? What Oot did was to measure this right hand side using tracers, like the stars which are numerous and easy to measure, F and K giants actually. And giants you can actually see much farther. And what he did was he actually estimated sigma in stars and gas is about 40 solar mass per parsec square. And from this equation, he got a value of sigma of about 90 solar mass per parsec. This number is whatever he could get out there from all stars, from all gas. This is the number he got. But from this dynamical modeling, by using these tracer stars, he got a value which is more than double. So he said that there is something invisible which is contributing to the mass, uh, and we cannot account for it. So this is like so this is what he did, and what we can actually do is uh, this sigma can actually be converted into a rho, and rho, using this value, obtained from the dynamical modeling, he got a rho which at the solar location was about 0.15 solar mass per parsec cube. This is the dynamical mass. So this is called Wood limit. This is the mass in the amount of mass which is causing gravity near the disk is this much. Okay, so we have actually yeah, we have actually done Jean's equation. I wanted to do one more topic, but I guess there is no time today, and this system is not also cooperating. Or maybe I do have some time. Because next time then I'll go on straight away to some simple pairs of solutions of the collisionless Boltzmann equation. So let me actually write down what I want to do. I want to do virial theorem. So okay, so we had the collisionless Boltzmann equation in 6-dimensional phase space. We have Jean's equations, which are in real space. Uh, we want to make further simplification, that is average over all the space and get some global quantities like the total energy and so on. Okay, and virial theorem is the approach to go towards that. So let's see. So let's write down the rho Vj. Okay, what I'll do is I'll abandon writing here and I'll just write on the board. Okay. Okay, so you have rho Vj bar. I'm just writing the Jean's equation, the way we derive it, rho Vi Vj bar minus rho dou phi dou xj. This is your so then so this is my Jean's equation. What I want to do is xk d3x. So I am integrating my Jean's equation over the whole volume, but with the factor xk. So I will actually have a vector equation. So let's look at this equation, this term. What does this give you? That would be just minus xk d3x rho dou phi dou xj. This is actually wkj. So you see kj, and this is called the gravitational energy tensor. Energy tensor. And it's symmetric. It's equal to wkjk. I mean, you cannot see that it will be symmetric in J and K from here, but uh, uh, what you can do is you can write phi, right? You remember phi equals minus G rho by x minus x prime d3x prime, right? This is your potential. If you plug that in there, and if you do manipulations, you will get an expression which I'm actually writing here. Uh, uh, right. So if you plug that in there, you will have a double integral d3x prime, and x prime are dummy variables. If you switch them, you should get the same expression. So this is the step to get to what I'm writing there. I encourage you to do it. It's just a little manipulation of these uh, double integral. Okay, so this is actually equal to minus g by 2 double integral rho x prime rho x xj prime minus xj xk prime minus xk by x minus x prime cube d3x d3x prime. Got it? Now you can actually see kj and jk. This is manifestly symmetric. Here it's not obvious that this is symmetric. Okay, so if you use this, if you plug that in, if you have this double integral, and if you do this trick of interchanging x and x prime, you get this. Okay, this is gravitational energy tensor. So this we have taken care of here. What about this term? So we have xk dot of xi rho vi bar vj bar d3x. This is an integration by parts, right? So you make it a total derivative. The limits are 0, and then you have dot of xi xk, which will give you delta ik. So this would be minus integral delta ik rho vi vj bar d3x. So this is simple. This I becomes k. Right, so it's kj. So I should not appear here. So I'm assuming Einstein's summation. I is summed over. So what you have is just do this. Now this is equal to minus twice k kj. This is kinetic energy tensor. It sort of obvious looks like kinetic energy. And half of that is kinetic energy tensor, is kj. Okay, and this can actually be, this has two components. One is the bulk part and the fluctuations part again. So this is nothing but kj is nothing but t kj plus pi kj by 2. So this is the bulk velocity. This is energy in fluctuation. This is energy in bulk motion. So let me write down. So so this is half rho vj ek bar d3x. This is equal to rho sigma jk square d3x. Again, this is symmetric. Okay. Again, this k is symmetric. So this integrated over gives you these kinetic terms. This integrated over gives you gravitational energy tensor. What about the first term? What about the first term? So let's see. The first one is here. So this is d dt. integral d3x rho xk dk bar. This is your first term. Right. See, d dt, x and t are independent, so it can just come out nicely. Right. Okay, so this actually is equal to twice d jk plus pi jk plus w jk. Now this is symmetric in j and k. This is symmetric. This is symmetric. So this must be symmetric. It does not look manifestly symmetric right now, right? If you change j and k here, these numbers remain the same. So this must also remain the same. This should be equal to d dt integral d3x rho xj dk bar, right? So we introduce something called the moment of inertia tensor. I jk is equal to integral rho xj x k d3x. So this is rho is a function of space, and then you're taking moments in space to get the moment of inertia tensor, and half of d dt of I jk is equal to half of integral rho xk x. And x are coordinates. They are independent of time, so you don't have to do derivatives in that. And this is from G's equation, of course, is half log of xi rho bar continuity equation. Minus sign. Now again, you make this a total integral, integration by parts essentially. So what you'll get is half rho v I bar xk delta ji plus xj delta ki dx. And that's nothing but right. So that's it. Right. So this is nothing but xj. So this will give you right. So half of integral rho dk bar xk. I think this one plus k bar x bar. So this should become k. So this is your half di dt, ddt of I jk. This is nothing but the sum of these two. Oh, no. That has a time derivative in it. That has a time derivative in it. It does not. So you have half of d2i jk dt squared, which is equal to twice t jk plus pi jk plus w jk. So this is the equation that you got. It's sort of an energy, a global energy equation. You have integrated over velocity, you have integrated over space. This is the rate of change of moment of inertia tensor. This is the bulk kinetic energy. This is the fluctuating kinetic energy. This is the potential energy. So this is some sort of a tensor energy conservation equation. Yeah, you are actually familiar with the simpler form of it, but this is so it connects the kinematic and morphological properties. Morphological properties. How is mass distributed in space? Kinetic properties. How is the velocity? Morphological properties. So it connects the global morphological properties and kinematic properties of the galaxy. Sir, yes.
In second line, you in final time you should write half of minus half of integration of d. Yeah.
Yes.
That line, that line.
Here to here, integration by parts. You take this inside.
But on where d comes? Yeah.
Huh? Okay. So this one.
Yeah, yeah, rho and xi and xk, then
This
dx by dt.
Dow rho dow t equals minus dow xi dow rho vi bar. See, this one is just that. Xj xk is just there. And this is just the time derivative, so right? Yeah. Okay.
So you use chain rule to make the time derivative into a space derivative. Del del x rho times v, then you need partial. We take it by parts.
No. This yeah. After this, from here to here, I'm doing chain rule. That's why this negative sign becomes positive. Right? So integration by parts. Either this is integration by parts, but what I think of it is just take this inside, and that term when integrated over.
Before that step, there is a time derivative of density.
That's correct. So that is here.
You made a space derivative.
Yes, that's correct.
Yeah.
Right, this is this is also a Jeans equation, right? Yes, correct. So if you take the trace of this vector equation, that's also valid. The trace of this equation will be, half d2I by dt squared plus twice k plus w is equal to, right? So this is what you get. This is the usual virial theorem that you have looked at. And if the system is steady, the moment of inertia does not change in time, the mass distribution does not change in time, this you set to 0, then you say that for a self-gravitating system, the sum of twice the kinetic energy, it includes both the bulk kinetic energy and the random kinetic energy, total kinetic energy, plus the potential energy of the system should be equal to 0. Or total energy is equal to minus W by 2. It's a negative. Now for a bound system, energy is negative, and W by 2, and this is equal to kinetic energy minus. And we apply this all the time, but this comes here. So how do we use it? So there's something called gravitational radius that's equal to Gm squared by W. Right. So Gm squared by Rg equals W. This is the definition of this gravitational radius. So you measure for example, in a globular cluster, you measure the velocity dispersion v squared, you know its size, so you can actually get its mass from the virial theorem. Okay, so it also gives you a sense of the mass content of the system. This is one of the ways in which you can use it. So actually, virial theorem is quite an important thing to be aware of. Now, say we think of a system like Milky Way. Okay, it's sort of virialized. If it should satisfy the virial theorem, uh, so it should have a total negative energy, right? It's a gravitationally bound system, uh, but the material that came early on, which now composes the galaxy, sort of came from very far away. It was like a zero energy system. Now it has become negative energy, right? Total energy is potential energy by 2. It is a negative energy system. So where did that energy difference go away? Basically, what it means is that in order for a system which is uh, non-interacting, for a system which is non-interacting to become bound gravitationally, you need to lose energy so that your total energy becomes negative. That energy can be taken away in form of radiation, or that energy can go and be carried away by some stars, which go out to infinity with positive energy, leaving negative energy behind for the system to become bound. So, for example, for matter accreting onto the black holes, virial theorem applies. If you have a steady accretion disk, so you bring matter from far away, and in order for it to you to put it in a steady Keplerian orbit, it has a negative energy in that steady Keplerian orbit. It started with zero energy. All this energy uh, that's released, right? So its energy is minus gm by 2r, right? If r is the radius at which it's circulating, the plus gm by 2r per unit mass has to be dissipated. It can go into radiation. That's why accretion is such a powerful source of energy in the universe. You are taking a test particle at infinity and putting it in a closed orbit near the potential where the velocities are of order c. You're essentially extracting a good substantial fraction of mc squared for every mass that you put in orbit very near the black hole. All that energy goes out either in radiation, all this quasar activity and all that, uh, or it can be retained as the thermal energy of this particle. So it can be hot and puffed up. So in that case, the kinetic energy plus potential energy, then in that case total energy will be zero. It's sort of weakly bound in that case because it has rotational energy and the uh, thermal energy, which makes it almost weakly bound. Okay, so these are sort of the things that you should be aware of. Sorry about today. This